Hello, my name is Gia, and welcome to my Lab 3 report on circuits for Physics 2212. First, I will go over the introduction and purpose, then some fundamental physics concepts, then part A and B of the experiment, and conclude with some further understanding. The purpose of this lab is to utilize the conservation of energy and charge and the definition of steady state to predict the behavior of circuits with resistors in series and parallel and the behavior of ohmic resistors and capacitors. The values will be recorded by voltmeters and ampere meters. Some fundamentals include the conservation of energy and charge, the circuit laws, which include node rule and loop rule, stating that current in equals current out, and the net charge and voltage of a loop is 0. Ohm's law, which states change in voltage is current times resistance. And finally, the capacitance equation, which is equal to the electrostatic constant times area divided by distance. Additionally, some important ideas to keep in mind throughout is that the system is the circuit and the surroundings is everything around it. The experiment was conducted in a FET circuit construction kit simulator where the wire resistance and ampere meter resistance were negligible. For part A, here is a visual of the circuit used, which is composed of two 1.5 volt batteries, 2 ampere meters, and 2 unique resistors. Current 1 and current 2 were both found to have 0.02 amps. And using the voltmeter, the change in volts was 3. When I use a voltmeter across the 47 ohm resistor, it found 0.96 volts, and across the 100 ohm resistor, it was 2.04 volts, which is consistent with Ohm's law. This is a diagram showing the potential differences, which show how a loop net potential difference ends up being 0. Some questions to consider are: when the voltmeter is attached, why doesn't the ampere meter reading change? This is because the voltmeter has a high resistance, causing very little to no current flow. Additionally, what happens when the ampere meter is connected in parallel with the 100 ohm resistor? Then both ampere meters read 0.06 amps. For part B, I modeled two circuits, one with a 10 ohm and one with a 20 ohm light bulb, and both with a 200 millifarad capacitor and a 9 volt battery. I measured the time it took to charge and discharge the capacitor for each circuit, in which the one with the 10 ohm resistor took 29.6 seconds, and with the 20 ohm resistor, it took 58.3 seconds. The graph on the right shows the natural log of the voltage against time. Some questions to consider are: what happens to the light bulb when a battery is connected to the RC circuit? The bulb starts very bright and dims over time until the capacitor is charged and the current stops running through the circuit. Then, consequently, what happens when the light bulb is connected to the charged capacitor in series? The same as with the battery, hence the capacitor acts as a weak battery. Now, for some further understanding, what if I did this lab in real life and use an actual ampere meter instead of an ideal simulated one? What is different about a real ampere meter, and how would it affect the readings of the circuits I hooked it up to? Well, a real ampere meter has resistance that would not be considered negligible and thus cause the currents to have less amps. Following, what if I did this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge? How does that compare to the real life? The ideal model simulator would predict that the capacitor would charge instantly. However, in the real world, there would be resistance in the wires and the battery, which causes it to take more time. Thank you for watching.